Have you ever thought about the periodic table of elements as like an exclusive VIP nightclub? Well, today in this explainer, we're going to build a definitive VIP tier list for chemistry. And specifically, we're looking at exactly what happens when different metals are introduced to something as simple and incredibly common as water. Okay, let's dive into this. I want you to picture yourself holding a solid piece of metal and just casually dropping it into a beaker of water. What happens next? Does it just sink straight to the bottom like a rock? Does it float? Or does it literally violently explode right in front of you? Well, the fascinating answer is, it depends entirely on where that metal ranks on our reactivity tier list. So we're going to break this all down step by step today. We'll start with the basic rules of engagement, look at the explosive metals, check out the ones that demand hot water, meet the steam squad, and finally, look at the royals who just don't care at all.
Right, let's get the absolute basics out of the way first so we know what we're looking at.
Whenever a metal actually successfully reacts with water, it basically follows this core three-step equation. You take your metal, you add it to water, and it forms either a metal hydroxide or a metal oxide. And, this is the crucial part, it always releases hydrogen gas. You can think of this as the basic script. But here's the secret. The metal's unique personality completely changes how intensely or violently they act out that script. So let's meet the heavy hitters at the absolute top of the list, the ones that go crazy in cold water. Meet the true divas of the periodic table, the alkali metals, specifically sodium and potassium. These guys are so intensely reactive that the second they touch even freezing cold water, the reaction is violent and highly exothermic. That just means it produces a massive amount of heat. In fact, they produce heat so incredibly fast that the hydrogen gas being released instantly catches on fire. They're so explosive that you can't even leave them sitting out on a table in the open air. In a lab, they literally have to be locked away, submerged in kerosene, just to stop them from randomly catching fire from the moisture in the air. Crazy, right? But, not all metals in this top cold water tier are total pyromaniacs. Take calcium, for instance. Calcium is definitely going to react with a cold water bath to form calcium hydroxide and hydrogen gas, sure, but it does it way more calmly than sodium or potassium. There's no instant fireball. Instead, it does something you probably wouldn't expect a piece of solid metal to do. It actually floats. I mean, it's a heavy metal, but as it reacts, all those little bubbles of hydrogen gas we talked about start to form, and they actually stick directly to the surface of the calcium. It's like they're acting as tiny little life preservers, physically pushing this heavy, solid piece of metal right up to the surface of the water. It's super cool to watch. All right, let's step it down a notch and look at the metals that need a little more persuasion. Enter magnesium. Magnesium is kind of like that slightly picky VIP. If you drop it into cold water, absolutely nothing happens. It just stares at you. It has a very strict demand. No cold water allowed. But the second you heat that water up, magnesium snaps awake and happily starts to react. And this just brilliantly shows how perfectly consistent our chemistry rules are once the metal's conditions are actually met. When magnesium finally gets that hot bath it demands, it does exactly what we expect. It forms magnesium hydroxide and releases hydrogen gas. And just like calcium, it pulls off that awesome floating trick. The sticky hydrogen bubbles cling onto the magnesium, lifting it right to the top of the hot water. Okay, moving further down the list, we've reached the tough guys, the ones that need a lot of energy.
Think about a classic lab experiment to really visualize this. You've got a glass tube, and shoved in one end is a wet sponge. You blast that sponge with heat to generate pure, energetic steam. Then, you force that steam over samples of aluminum, zinc, or iron. It's only then, under the intense energy of that steam, that these metals finally decide to react. And we know for sure it's happening because if you run a tube from that setup into a tank of water, you'll suddenly see those unmistakable bubbles of hydrogen gas rapidly popping up. But here is a massive chemical plot twist for you. Up until now, every single metal we've talked about formed a metal hydroxide. But this steam squad, aluminum, zinc, and iron, when they finally do react with steam, they completely bypass hydroxides. Instead, they form metal oxides alongside the hydrogen gas. So aluminum becomes aluminum oxide. It's a really fundamental shift in the script, all because of the lower reactivity of these specific metals. Finally, we reach the bottom of the list, the absolute elite.
These are the metals that are just so incredibly stable, so unbothered by everything around them, that they completely ignore water entirely. Lead, copper, silver, and gold. You can drop them in ice water, you can boil them, you can blast them with steam until the end of time, and their chemical structure literally will not care. Zero reaction. And honestly, this incredible, stubborn stability is exactly why we rely on copper for the pipes in our houses, and why gold and silver make perfect jewelry that lasts for hundreds of years. So let's look at the big picture here. See how beautifully we just stepped down the thermometer of reactivity? We started with the fiery explosions of sodium and freezing water, stepped down to magnesium, stubbornly demanding a hot bath, went further down to iron, holding out for high-energy steam just to form an oxide, all the way down to gold sitting at the bottom, entirely unfazed by any of it. It's just a perfectly logical, beautiful scale of chemical behavior. But this leaves us with a pretty fascinating question to think about. If our unreactive royals, like gold and silver, can just brush off boiling water and high-pressure steam, what extreme, crazy chemical combination does it actually take to break them down? Well, I'll give you a quick hint. It takes a highly corrosive, custom-mixed cocktail of powerful acids called aqua regia. But as for how that intensely destructive mixture actually works, well, that is a fantastic topic for our next explainer. Thank you so much for hanging out and learning with me today. Stay curious and keep exploring the amazing world around you.